Hello and welcome to Bic Gardner's Office Hours. Today we'll be talking appearance theory with our Senior Application Specialist, Corey Cohen. If you're unfamiliar with the Office Hours format, we will have a brief presentation, maybe 20 minutes, on appearance theory, and then the time is yours. We'll open it up for questions, discussions, comments, anything you'd like, anything we can help with. If you have a comment or question, just log it in the Q&A box located in the bottom right-hand corner of your screen. We are also recording this presentation, and as a follow-up, we'll send the link as well as the presentation materials to you tomorrow during those follow-ups. So with that, Mr. Cohen, take it away. It's all yours, sir.
Thank you, John. Good afternoon, boys and girls. Thank you for coming. Today we are talking about appearance theory, specifically appearance of high gloss surfaces such as automotive paint using our WaveScan instrument. So you may use common terms like orange peel or DOI for discussing the appearance of high gloss materials. And we're going to show you how those parameters can be measured and quantified using this instrument. So uniform appearance equals quality. It's very important for consumers to see a consistent appearance. That's going to make them want to buy something. They're going to associate that consistency with quality, and it's going to make them want to buy it and spend more money on it. So some things to think about when painting materials or painting products and how that can affect the appearance. Surfaces painted in a horizontal versus a vertical position can have different properties to them depending on how they're painted. Body versus add-on parts. So typically the body of a car will be produced by the automaker, and often the add-on parts, meaning the bumpers, the door handles, the mirror housings, things like that, are often made by OEMs or third-party companies that will produce those parts, sometimes out of different materials than the rest of the body of the car, and have to paint that to match the rest of the car, sometimes using a different paint system the rest of the car is being painted with. So it's important when all those parts come together, and this isn't just for cars, this could be vacuum cleaners, laptops, things like that, appliances. When all those parts come together in the finished product, they all have to look good next to each other. Another consideration, as mentioned, various substrates. Sometimes you're dealing with steel, sometimes you're dealing with plastic, and different coating systems can look slightly different. So it's important that everything sort of looks good when placed next to each other, when you're able to view them next to each other, and it's easy to see those small differences. And so you need a stable process to guarantee quality over time. So appearance is influenced by things like waviness. These are sort of the macro structures in the surface causing this waviness. So here we have an example of two surfaces where these lines of light are being projected onto it, just so you can see better see the structure of the surface. And so one of these surfaces is kind of smooth; those lines are fairly smooth, and in the picture on the right, that surface is a lot more wavy and is exhibiting what we would commonly refer to as orange peel. And then we have brilliance, or DOI, and this is an effect of the very small microstructures in the surface causing a diffusion of the light. And so on the left here, in the left image, we can see a very low brilliance, low DOI, or distinctness of image is what that stands for. The contrast is very low on the left. On the right, and that's much more brilliant, better DOI, better contrast. So orange peel is caused by this wavy light dark pattern, which happens, it's caused by light shining on the surface and then reflecting off in various directions due to the macro structures in the surface. So this isn't really a diffusion of the light so much. This is just, different parts of that light beam sort of being scattered at different angles depending on the hills and valleys, the waviness of the surface, and that's what's causing this wavy light dark pattern in the surface as seen in this image to the top right. So here we have two samples viewed at different distances. So at that 40 centimeter distance, we can better see the microstructures in the surface. So we're seeing more the smaller structures in the surface, and that's causing this sort of sandy effect, you might call it. And on the right, if we step back a little bit to a distance of 3 meters, now due to the resolution of the eye, we're seeing more of those larger structures, and that's going to cause that waviness that we refer to as orange peel. And so just as an example of, kind of a analogous visual here, when we're looking at something up close, when we're looking at these letters at a very close distance, as in on the left, we can make out the individual letters. But as we step back and we get further and further, we're not really seeing the individual letters so much. We're seeing kind of just the pattern that they form at a macro level. And so it's kind of, on the left, you're seeing the trees. On the right, you're seeing the forest. And both are important. You're going to see different things about the surface depending on how close or far away you're standing from it. So again, the resolution of the human eye, at 40 centimeters, we can best see waves or structures at about it peaks at about 2 millimeters. So this is not wavelengths as in wavelength of light. This is wavelength as in the size of the structures or the waves, the waviness in the surface. So at 40 centimeters close up, we can best resolve the structures about 2 millimeters in size. And when we step back to 3 meters, the optimal, our eyes, the resolution of our eye can optimally pick out those structures somewhere between about 15 and 20 millimeters. So that brings us to our WaveScan instrument and the measurement principle. So the way this works, it uses a laser light source. It reflects that laser light off of the surface, and it measures the deflection of that laser to create this optical profile. So this is a rolling instrument. It's a moving instrument that you actually roll across the surface. As such, so as it rolls across the surface, the waviness in the surface, the structures in the surface are going to cause that laser light beam to deviate, and the sensor is actually detecting the positioning of that laser, the reflected laser, rather than like a spectrophotometer or a gloss meter where it's detecting how much light is reflected. This is detecting the deviation of that light. So you take that optical profile and you apply some, or the WaveScan, I should say, applies some mathematical filters in order to separate those structure sizes into the surface into what we call short wave and long wave. And so just as a relative thing, know that higher short wave and long wave mean more structure in the surface, which is generally considered bad. You generally want less structure in the surface, so it's a smoother looking surface with better DOI, better brilliance. So higher numbers are typically considered bad for short wave and long wave at least. So here we have a couple examples of surfaces with different short wave and long wave measurements. So in the top, in sample A, we have a short wave value of 15, and we have a long wave value of 10. So pretty low short wave, pretty low long wave. We're not seeing a ton of waviness in the surface. We're not seeing very low DOI or low brilliance. The contrast here is pretty good. But then we look at sample B, and now the short wave is 17, so not too much different than sample A. But in this case, the long wave is 31, so it's a lot higher here. And so the waviness becomes much more apparent, and you're going to see a lot of that orange peel effect in the surface. But now here we have two surfaces that do look very different. And one is exhibiting a shortwave value of 21, so a bit higher in the shortwave, and a long wave value of 7. And we can see a good bit of waviness here. And then the bottom, we have much lower shortwave, but we have higher long wave. And so that's also exhibiting a good amount of waviness. But it does look pretty different than the sample up top. So it was concluded after the first generation of wave-scan instruments that shortwave and long wave weren't really enough. We need to resolve more categories of structure sizes in order to better assess our samples, assess our products. And so for that, that optical profile was split into a number of different categories that we refer to as the W values, W, A, B, C, D, and E. And these have specific ranges. WA goes from, that's the amount of structures in the 0.1 to 0.3 millimeter range. WB is the amount of structure in the 0.3 to 1 millimeter range. WC is 1 to 3. WD is 3 to 10, and WE is 10 to 30. So not only are we resolving the structure in the surface into more categories, but we're also expanding the range, whereas shortwave and long wave, those two scales only go from about 0.3 millimeters to 12 millimeters. WA through WE expands that range to about 0.1 to 30 millimeters. So now we have what we call our structure spectrum, which is the structure of a surface mapped or graphed as the WABCDE values. And again, we have two surfaces here, the same two surfaces, sample C and D. And we know the long wave values for both, but now we're also getting additional information with this WABCDE values, and that's going to tell us a lot more about the surface. So DOI again stands for distinctness of image, and here we have an example of two reflected images, one with good DOI on the left and one with poor DOI on the right. So of course, this is also something that we want to be able to measure and quantify. And these are just some sort of synonyms or other similar words for DOI: contrast, sharpness, distinctness. So the influence of structure on distinctness of image. So we have light scattering, which is causing a contrast and reduction, and that's being caused by those very fine microstructures less than 0.1 millimeters. And then we have the smaller structures between about 0.1 and 1 millimeter, and those are causing a distortion of the outline. So there's very, very fine structures causing contrast reduction. The slightly larger structures, but still in the shortwave range, cause a distortion of outline. But we can see here, remember those WA through WE scales start at 0.1 millimeter. So just using those scales, we don't have anything that can see or measure structures in the smaller than 0.1 millimeter range. And so that's why the dullness measurement was developed. Now, if you're familiar with reflection haze, this is kind of a similar measurement. It's how much the surface is diffusing the light as it's being reflected off. And the way this measurement works is that you have the instrument, the WaveScan, is going to project a circle of light onto the surface, and it's going to measure how much of that light is reflected back outside of that circle. So here we have these two concentric green circles here. The inner circle is where the light is projected, and then as that light scatters, it will be detected in that outer circle. And so the dullness value is the amount of scattered light, the amount of light that's detected in that outer circle divided by the maximum possible amount of scattering, and that's referred to as the dullness value. So one of the great things about dullness measurement, unlike gloss measurement, dullness is both independent of the material, the paint material. So with gloss, different materials with different refractive indices can't be compared with each other because they're just going to measure differently. With dullness, that's not the case. You can measure different systems, different paint systems with different refractive indices, and you can get comparable results with them. And the other benefit is that it works equally well on curved and flat surfaces, which again, curved surfaces can be an issue for gloss measurement, but not for dullness. So this gives us our complete structure spectrum, not only the WABCDE for structures in the 0.1 to 30 millimeter size range, but also dullness, which gives us an indication of how much structure there is in that less than 0.1 millimeter size range. And now distinctness of image, the DOI scale, is a function of the dullness as well as the WA and WB. So the larger structures, the WCDE, don't really have an effect on the DOI of the surface, but the DOI is largely affected by mostly dullness, but also WA and WB. So the WaveScan is a QC tool to document appearance and recognize changes early. You can use it to measure substrates. You can use it to analyze things like substrate quality and process parameters. So typically a paint system might consist of a number of different layers, E-coat, primer, base coat, clear coat. Sometimes there are fewer, sometimes not, but each of these layers is going to have an effect on the final appearance of the overall coating. And the WaveScan can be used to sort of detect what's going on due to differences in different layers. So for example, we have a study on the effect of waviness caused by the steel that's used. So here we have glass as a control, and we have 3 different types of steel. And this is showing the waviness of the final paint. Presumably these were identical paint systems. All these surfaces were painted identically, and then the final product, the finished coating, tested. And you can see that there are some pretty drastic differences just due to the type of substrate. So glass being very, very smooth is going to have the lowest structure, very low shortwave and long wave. The other 3, the steels that were tested here, the long wave is changing somewhat, but most of the difference we're seeing is actually in the short wave. So this is showing us that the type of steel that's being painted can have a very significant effect on the waviness of the painted surface. So here's another example. So here we have a surface. So this surface at the top doesn't look very good. It has pretty high short wave, pretty significant long wave. It's giving a kind of a sandy look with poor DOI. And so one thing you can do to improve the look of that surface is by sanding the primer. So sanding the primer and then applying the top coat and the clear coat on it is going to cause that surface to have a much better wet look. It's going to look smoother, better brilliance, better DOI. But now we're seeing a bit more waviness in the surface, where the top we're kind of, we are getting poor DOI and kind of a sandy look. Once we sand that primer, that sandy look is going away, but now we're getting sort of a wavy orange peely look to it. So this is showing the influence of flash-off time on appearance, so how long it takes the coating to cure in an oven. And so we have two surfaces here, a hood, which is a horizontally painted surface, and then a door, which is a vertically painted surface. So we can see the influence of the flash-off time on each. So with the hood, when the flash-off time is longer, that's going to increase the short wave by a good bit. Not too much effect on the long wave, but it's going to have a pretty significant effect on the short wave, because remember, this is a horizontally painted surface. So now when we look at the vertically painted surface, that door, that longer flash-off time is going to have a pretty similar effect on the short wave, but it's also going to have a much more significant effect on the long wave because it is a vertically painted surface. And while that coating is waiting to cure, it could be experiencing some sag, which could cause higher long wave structures and more orange peel on the surface. So here again, we have two surfaces, one painted in the vertical and one in the horizontal position. And you can see that the short wave is pretty much identical. The dullness, WA, WB, they're pretty much identical between these two surfaces. But once you get into the longer wave structures, the WC, the WD, WE, you can see that that baking position is going to influence heavily the amount of long wave structures in the surface. And here we have some influence of clear coat film build. Here we have several different clear coat film builds, 16 microns, 24, 30, and 50. And we can see that as the film build increases, again, the short wave is not really affected, but the long wave is drastically affected by that thicker clear coat. With each added thickness for each layer, it's bringing the long wave way down. So here are just some examples of what you might see in a surface and what might be causing it. So if the dullness is too high, that could be due to a milky clear coat, which could be caused by a dry spray or something like that, or it could be the material itself. If the WA is too high, that's often substrate influence, or similarly, it could be that clear coat in a dry spray. If WB is too high, that is often substrate influence. WC too high could be caused by insufficient clear coat film thickness. We saw that in the previous slide, where as the clear coat gets thicker, those longer wave values are going to go down. So if it's insufficient, that can cause the WC to be too high. It could also be caused by sanding marks or the paint spray as well. And if WD is too high, that is, again, often an effect of insufficient clear coat thickness or a very rough substrate. So plenty of process parameters to watch out for that could influence the final appearance of the surface. Things like the distance of the sprayer from the surface, the voltage, the film build, the flash-off time. You can add additives to improve some of this stuff. So there's a lot that goes into making a smooth, clean, good-looking surface. So here we have, again, an example of a surface exhibiting very high shortwave and very high long wave. And so one way you can improve that is to, again, optimize the clear coat application. So you increase the clear coat film build, and that's, again, not going to have much of an effect on the short wave, but it could bring the long wave way down. Excuse me 1 second. Thank you. Forgive me. Okay. So increase the clear coat film build, and that can decrease the amount of long wave in the surface. But it's still getting this sort of very sandy look with the low DOI. And this is actually the image we saw before, where the long wave has been brought down a bit, but it's still exhibiting a lot of short wave, giving that undesirable look. And so if the primer is now sanded before coating, that's going to bring the short wave way, way down and give us a more brilliant look with better DOI. But that is, again, going to reveal more of those long wave structures, and we're going to see more of that orange peel. So what we can do then is optimize the primer and or the top coat application to actually bring that short wave back up a little bit to better balance out the long wave. So really, in the end, it's sort of a balancing act. Now, obviously, ideally, it would be great if you could eliminate all structure in the surface. That would produce a very, very smooth-looking surface with excellent DOI and zero orange peel, but that's not really practical in a production setting. So what you can control for is sort of the relative amounts of the short wave structures to the long wave structures, because they do sort of cover for each other to a certain extent. So if the short wave is too low, even a little bit of long wave can make the surface look very orange peely. If the long wave is way, way too low, even a little bit of short wave can make it seem a bit sandy, and the DOI can be poor. But if you balance both of those things, you can get a better looking surface. So one thing that's necessary to measure, as mentioned, often door handles, mirror housings, fuel doors, things like that, are often fabricated and painted by third-party suppliers to the automotive industry, and those need to be measured with the wave scan to make sure that that they look good as well. The problem is that it's such a small part that the size and the curvature, the standard size wave scan unit can have an issue measuring such small parts. And this is why we developed the microwave scan unit. This is for use with small and curved parts. So one of our newer units, it's called the WaveScan Dual. And the reason it's called the Dual, this is as opposed to the old WaveScan DOI, or one some of you might be more familiar with, the WaveScan 2. So the older WaveScan models can only measure up to a dullness range of 40 dullness. So if the dullness gets too high, the measurement principle of the wave scan sort of breaks down, and you don't get good measurements at a very high dullness range. So traditionally, the optimal range for measuring surfaces with the wave scan was up to a dullness of 40. And you could measure surfaces between a dullness of 40 and 55 if you turn a property called plausibility off. But the measurements you get there aren't quite as good, and certainly not comparable to the measurements that you get in the very low dullness range. So if you are measuring in that sort of questionable yellow range, you can get good values there, but you should really only be comparing those values with other surfaces of similar dullness. But in contrast to that, we have the WaveScan Dual, which has a dual light source that allows it to measure at higher dullness ranges. So the optimal range for the WaveScan Dual is up to 65 dullness. And then if you turn the plausibility off, you can actually get up to 80 dullness. So this was developed to allow for measuring things like primers. We also have a robotic base scan unit for non-contact measurement right on the production line, hands-free. It's all done by robot, very precisely positioned, and you can get good measurements even on a moving line. And then we have the brand new generation of WaveScans, the WaveScan 3 and the WaveScan 3 Dual for measuring those higher dullness surfaces. So this is a very recently released instrument. It has a pretty nifty color touchscreen. It's a bit easier to use than the older model. I don't want to bash our old WaveScan Dual because it's a very solid instrument. But it was developed a good amount of time ago, and the screen, the controls aren't always very easy to use. So this new model has a color touch screen similar to our new Spectra 2 guide instrument, if anyone out there has ever used one of those. The controls are much easier, and it allows for certain things that the older WaveScan models didn't. For example, you can do a quick check, which is just a quick measurement of a surface without having to activate a memory or an organizer, without having to save the data and then delete it later. If you just want to take a measurement and just see some values, this new unit allows you to do that. It also allows for pass-fail right on the instrument screen, so you can program tolerances into your standards, and it will actually tell you immediately after measurement whether your surface passed or failed based on those tolerances. It also has optional Wi-Fi for cable-free data downloads. You can protect your configuration with a password. It has a new slim docking station, so that's going to take up less space on your desk. It's going to automatically charge the batteries, and it has a direct connect USB port to transfer data to a computer directly. Our previous models, you had to have the docking station present in order to transfer data. The new one, you can connect it directly. If you're wondering about the correlation between this new model and the previous models, the correlation is pretty much perfect. The measurement principle is very, very solid. There was no need to really change that in any significant way. And so the readings that you get with this new generation of WaveScans, you can expect it to match up very well with the older generation of WaveScans. So that's it for appearance theory. Believe it or not, we did not go very much in depth into a lot of these topics. There's a lot more to discuss when it comes to appearance theory and WaveScans. But just wanted to give you a surface level overview, and now we will open the floor up to questions if you want to know anything specific.
Thank you, Corey. Good stuff here. We do have a handful of questions here, and if you have questions that are still out there, please log them in the Q&A box, and we'll get right to them. First question by Mitchell: is the scattered light represented by the outer green circle? That may have, I think, towards the middle of your presentation, Corey, you may be referring to a specific slide you showed.
I'm sorry, can you repeat the question one more time?
Sure. Is the scattered light represented by the outer green circle?
Yes. Yes, it is.
Okay.
Here we go.
There's two different things.
Yeah, so the inner green circle is where the light's being projected, and the outer circle is what would be considered the scattered light. It's the amount of scattered light that is directly related to the dullness value.
Okay.
So that's
Mitchell. Oh, go ahead.
it's not the whole wave scan.
What's that?
Your audio is breaking up a bit, Ray. It's breaking up a little bit. You want to try again?
Can you hear me now?
Yes, much better.
Okay, so that's only for dullness, this value. The other is laser technology that goes across the whole surface. So this is only for dullness, just to be clear.
Cool.
You
Thank
want to
you.
unmute him and
Yeah, Mitchell, I'm going to unmute you. Did that answer your question, sir?
Yes, it does.
Are you
Thank
there?
you. Yeah, I was just
Great.
confused with the yeah, this is Mitchell. I was just confused with
Okay.
the equation. So I was wondering what the scattered value was in that equation and how it was represented with the circle. Thank you.
Okay, excellent. Thank you. Next question here from Mike. For measurement accuracy of the laser and camera, is it recommended to only roll the wave scan forward when taking a measurement, or is it okay to roll backwards also?
It's generally preferred to roll forward, but you can roll backwards. Sometimes you do have tight spots that need to be measured, and you kind of have to roll back and forth to get the desired length. So it's acceptable, but not preferred.
Okay. Another one from Mike. Let me get this question answered, and then we'll unmute you, Mike, see if you have any elaboration or any other follow-ups. Are the mathematical filters similar to those used by the Cloud Runner? Are there major differences that can be shared?
it's totally different.
Okay. Mike, I will unmute you here. You there, Mike?
Yes.
Okay. Did that answer your question?
Yes, I'd always been curious about the first one in particular. Hi, Ray. I've compared myself, not extensively, but have gotten similar wavescan results rolling forwards and backwards. But I was just interested to know your perspective, so that helped a lot. Yes, I guess that does make sense, comparing the wavescan to the Cloud Runner. That, well, of course, all the structure sizes, they'll be very, very different. But yeah, I was just interested to know a little bit more about how the values are all filtered into the individual groups. But if it's secret, then that's okay.
It's not.
Is it tough?
It's that the Cloud Runner measures the lightness darkness difference, and the wave scan the texture. So
Okay.
they may correlate, but they're not meant to. Does that make sense?
Yes.
Okay. All right.
Okay, thank
Cool.
you.
Thank you, Mike. You bet. Okay, another question from Mitchell again. Can the wave scan dual measure E-coat, or is E-coat considered too dull, and the limit for dullness for the dual are surfaces with primer? Let me read that again.
The dullness for the E-coat is too dull. We actually have an instrument we're come out with that's gonna be able to measure E-coat. We can at this time sometimes measure some primer, like Corey was saying. You can turn off the plausibility. And sometimes you can measure some stuff that's dull. But at the moment, E-coat, no.
Okay. Is there any anticipated timing on when we'll be able to do that new device?
I mean, we thought it would be this year, and it's, with COVID and everything.
So probably 2022-ish. But
that's it.
All right, when that is available, you'll definitely all know that. That's for certain. Thanks, Ray. Let's see here, from Matthias. Where did you say the recording of this presentation would be saved to? Okay, we will send this out via email. The recording of this presentation, as well as this discussion, along with the presentation that Corey shared. We'll send that out to everyone on this call tomorrow morning. That's when it usually takes some time for the video to process, the recording to process. So you'll get that in your email tomorrow. What other questions, or are there commonly asked questions that people from Bitgardner typically get that we can bring up?
So the one question that was asked about, measuring back and forth, I would hope you could just change your scan length to 5 instead of 10 and be able to just measure one direction. Obviously, you can measure backwards with the Wavescan tool, but if you have like a micro, you cannot. Just a little clarification on that.
Okay. Good. What else, Corey? What do you get typically when people get into appearance theory?
I think one thing that comes up is that sometimes a spec will be based on one value, and people say, "Hey, we're hitting this value. It's within spec, but the surface looks awful anyway." And that's really partly it's the fact that what I was talking about before with the short wave and the long wave needing to be balanced. But also it's a lot of data. It's complicated, complex data that can't always be condensed down into 1 or even 2 or 3 scales. You often do need to look at different scales. And so the dullness, WA through WE values, are combined in so many different ways. We have, 30, 40, 50 different scales that are, just equations using those values for looking at different things. So if you're looking at, one scale and the numbers are saying your surface looks good, but you're looking at it and you can tell that it doesn't look good, often you need to start looking at some other scales that are going to tell you a more complete story about the surface.
And I have to say, or vice versa, if your surface looks good but your number's bad, then you really need to look at the structure spectrum, and you can totally send the data to us and we can look at it. I know that we worked on a project with GM where like the fascias, because of that micro crinkle in the substrate itself, cause the R value to be lower. And I think on most plastic parts, it's going to be a bit lower for the R value specifically. And you have to remember that these are calculated values that the OEMs decided that they wanted to use. We didn't necessarily come up with the calculations. We just matched what they wanted. So, I think that's kind of really important. So does anyone have any questions on that? I can't see, sorry, I'm not in the meeting all the way today, but I don't know who's on, so. Are there any part suppliers that have questions with the R value or the CF value? Because both of those are calculated and it can get a little wonky on plastic parts.
Corey or Ray, can you hear me?
I can hear you.
Yeah.
Can you?
Okay, good. Sorry, I'm having audio issues too, one of those days. Next question here from Joe. Will the Wavescan detect or measure chatter or washboard appearance in a painted finish which is caused by the metal substrate? These small waves are some 1 inch to 3 inches apart.
So I say no, Corey. I think
Yeah, it
it's too
sounds
small.
like no. I think too big. I think it sounds like those structures are too far apart for the wave scan to be able to quantify.
Okay.
So this is some of the stuff that we're trying to do with the new instrument is to be able to measure stuff like that.
Okay. Great. Another question from Mitchell here. Her organization only looks at LW, SW, DOI, and DU values. Would W values paint a better picture in terms of appearance data? And is this related to the issue I'm having where the color has great LW, SW values, but not so great DOI or DU?
So the DU basically comes from the color that you're painting. So if I have like a silver, I'm going to have a higher DU. If I'm painting a black, I have a lower DU. But the LW and SW really relate to what I see visually. You could also look at the balance and the structure spectrum would be my recommendation.
Mitch, I'll unmute you again here. Did that answer your question?
Sorry, what was the last thing that was said? To look at which values instead? I didn't really hear that because it cut off.
Oh, sorry, the structure spectrum. So if you look at DU through WE, that's better than long wave, short wave.
So DU and WE?
Yeah, the DU, WE. Hey, Corey, can you talk for a minute? Because my dogs are barking.
I can jump in there. This is a structure spectrum curve that Ray was referring to, and it's kind of like a reflectance curve for color. It'll tell you a lot more about what's going on than just your long wave, short wave, and dullness values. So depending upon the overall structure of your paint coating, you know, where you have effect pigment, what pigment layer it could affect it. If you have, you know, some heavy pearl in the clear coat, or if it's a tri-coat, all those things are going to affect the balance of all of these measurements. And that's what we start talking about balance in the curve. Typically, you want a little bit more WB than you want WD, because it helps hide the overall quote-unquote waviness. So if you think of this
And you
as...
want the WC to be lower than the WD. Like the structure that he's showing you right now is a good structure. You can see on the screen. Sorry, go ahead, Greg.
No, it's just what I was going to finish up with, is then looking at not only B and D ratios, but then how C and D play out.
Okay,
So
thank you.
In the other example that Corey had, where we had the film build example of the clear coat, you really want to balance that, because in that particular example, the highest film build for clear coat, although it flattens out your long wave completely, it's kind of a bang for your buck type of scenario. Almost doubling the amount of clear to get a very little decrease in C. And then when you have C that's slightly higher than D, that now all of a sudden, that's not good balance. So you'd rather have a lower C and a higher D for balance. Just as an example.
And it's also a money concern. You know, like you don't want to put that much part.
Good. Thank you. Another question here from Carol. She's asking about R value. Is the R value a reliable single value to use for a comparison tool and then back up with the full structure spectrum?
So the R value is basically based on long wave and a bit of short wave. And if you can unmute her and let me talk to her for a second, I just want to know what kind of part she's asking.
Yeah, let me. Okay, Carol, you are unmuted here.
Okay, I don't know if this works. Is this working?
Can you talk into the phone a bit more because it's hard to hear you?
I'm not on
Yeah.
the phone. Tell me if this
Oh,
is
on your
working.
Yeah, we can hear you. It's quiet. You're
Okay.
through your computer?
Yes. Yes.
Okay.
So yeah, we use the R value. We'll do like a scan, and we'll record that R value. And of course, we have the saved information that we go back into. But probably the R value is one of the main numbers that we'll pull. So there just wasn't anything in the presentation, and I was confused. Thank you.
So the R value is a calculated value based off of what the ACT panels looked at, 10 years ago, Greg, I think, or more.
At least, not more.
Yeah. So it's long wave dominant, and it doesn't have a lot of short wave in it. And if you're an add-on part supplier, it's a bit difficult to meet certain specifications. So I have to know more to give you more information. But in the end, you should always look at the structure spectrum and see what that looks like. I bet if you're an add-on part supplier that you're heavily long wave dominant.
Okay, well, actually, I'm measuring reinforced plastic RV sidewalks.
Would you mind repeating yourself again? That was very quiet on this end.
Sorry. What we're measuring are reinforced plastic RV sidewalls. So not an add-on part or a painted part, but a gel coat part. The whole sidewalk.
John, did you get that? Because I can't.
Yeah, I heard gel coat, but it's not an add-on part. It's a plastics molded piece.
Yes.
Is that right?
Well, right. An RV sidewall. The whole
RV
sidewalk.
Oh. Well, in general, I think we would agree that R value can be used as a processing kind of one number tool to flag you if things start to change. Since the R value has very little sensitivity to short wave compared to long wave, your short wave changes are going to come mainly from substrate changes. So if you have a lot of variation in your substrate, then we would definitely say you should be looking at both the structure spectrum and the R value at the same time, because you're going to see changes in your smaller structures if you have a lot of variation in your substrate.
Okay, thank you.
You're welcome.
Add-on part suppliers have a lot of shortwave, and it can affect the R value because of all like the pinch in the surface of the substrate. But I mean, for your specific application, I'm quite sure. I haven't dealt with it a lot.
I can also make another comment on that in gel coats, and in larger sample sizes, like in larger boats, the WE actually becomes very important because to view those larger objects, you're backing up to look at a bigger surface area, or if you're looking down the side of the RV itself, then you might be starting to see some longer waves. So I would definitely pay attention to the whole spectrum in that application.
Okay. Thanks.
Just
we
from
have-
my perspective. Oh, go ahead.
No, I was going to say, go ahead, Bray.
So from my perspective, the WB is very, and it really affects like how you see things visually, especially close up. So I think, you know, because maybe the R value is not giving stuff that you want, it could be that the WB is high.
Okay. I think we have one more question here from Nilo. How much distance does the unit have to travel to have good results? I have a project that I'm working on, and I just using the Trigloss meter to quantify gloss and may consider another instrument.
You'll have to unmute him.
Yeah. Nilo, I'm going to unmute you here. Are you
Oh,
there?
yes. Go ahead. Yes, I'm
Okay.
listening.
Yeah. Would you mind asking your question again?
Yeah, I'm curious to see to know how much distance that they need to travel to get good results. How much does it need to travel?
So the minimum for the dual is 5 centimeters. The micro can be used as like a point and play, but it gives you DOI.
Oh, okay.
So it just depends what you want, but 5 centimeters, and it really depends on the surface you're measuring.
Okay.
If you need a microwave scan or a wave scan dual. So that
I
would
believe,
be,
yeah, the non-micro probably will be best for the material that I'm working on. That will be great.
okay. Yeah.
All right, it sounds good. Thank you.
So
Okay.
one other thing to add there in terms of the 5 centimeter scan length as opposed to say a 20 centimeter scan length, you're going to get better repeatability with the longer scan lengths. And we typically want people to average, especially if they're doing a laboratory experiment, to get better repeatability on sample to sample or within a sample. So you really have to combine, if it's a smaller scan length, maybe you have to do more of those in order to get the same repeatability of a longer scan length with just a few.
Oh, okay.
And it's a pretty quick scan, so it's not going to, it won't kill you in terms of time. It just will add a few seconds to, maybe a half a minute more of measuring time.
Okay. Yeah, because sometimes our sample size varies from 15 to 30 centimeters, so I think we have sizable samples to scan. Okay. Thank you.
Okay. You bet. All right. I think that wraps us up for today. Thank you, everyone, for the great questions and for joining us. Like I mentioned, we'll send out a link to the recording tomorrow morning, first thing usually, along with the presentation materials. And if you have any questions, you can reply to that email or contact your regional salesperson at Vic Gardner or me in marketing. So with that, thanks for your attendance, and hope it was well worth the time. A lot of great information, and we'll see you at a future office hours or web seminar by Vic Gardner. Thank you.
Thanks, everyone.
Thank you.